Okay, hello everyone. Today we are going to talk about the precision time protocol (PTP) that is used for time synchronization within a network and the system that we have. And we are going to use the standard IEEE 1588 as the framework that defines the precision time protocol requirement and architecture. Now, before we start the main topic, I want to point out that uh, time synchronization and precision time protocol is not a luxury for your system. It's an absolute requirement when you have a system. We are going to talk about the application and why we care about that. But I want to point out that this is not a secondary kind of like aspect for when you want to like design the system or even work this with the system in the performance of the functional performance of the system. It is an absolute necessity. Now let's start with the question that why do we even care about the synchronization? Okay, so in most of the computing environment, timekeeping is a necessity, is not just a convenience. Okay, so when we have a distributed system, okay, uh, the synchronization, the time synchronization become a design constraint. Now, there are several domains that we could like use, for example, to see how important is the time synchronization. One would be like the industrial automation. When we have like robots and conveyor systems, they all should work in a precise temporal harmony. Okay, so for example, when we have like in a factories, when we have like a machine like robots and conveyor belts, they need to move in a sync with each other. Okay, so that the tasks are performed in a correct order and there is no delay or collision between those machine and the order of the task. Okay, so this is one aspect of like importance of a synchronization in like industrial automation. Now, another fact would be the control loops and the work with the sensors. So all of them require some timestamp alignment. Okay, so they behave like a coherent system. So when we have like a sensors and controllers in the control system, they need to know exactly when the data is collected or the command is issued. Okay, so the system could respond accurately and reliably. Now, the precision time protocol that we are going to talk about, that the PTP basically make the system able to have like a jitter free motion control. We could have a predictive maintenance logging or a real-time analytics. Now, when we use that precise timing through PTP, basically we can avoid the unexpected delays, which we call a jitter, and we can log and record all the conditions and all the measurement accurately so we could have a better maintenance. And basically, it gives us a real-time analysis ability so we could actually optimize or improve the performance. Now, another field that we could discuss and show that how important is synchronization, the time synchronization, is telecommunication. So consider the mobile-based stations. Okay, all of them should be aligned transmission slots. So and the precision should be within like hundreds of nanoseconds. So like the cell towers that handle the wireless communications, they have to transmit and receive the signals at a very high time precision. Okay, so they could avoid the interference and make sure we have a fast and clear connection. One example would be like a 5G, which requires phase synchronization to support the time division duplexing, the TDD, and in a situation that we have like a massive MIMO technologies. Now, when we talking about like for that example, the advanced 5G technology, uh, that technology like TDD, as we mentioned, or like a massive MIMO, the multiple antenna, when we have multiple antennas in our system, all of them should be aligned both in phase and time. That makes them able to communicate efficiently and kind of like without any overlaps. Now, another kind of like industry that we could mention that needs that time synchronization is smart energy grids. Now, we have an aspect named synchronophaser monitor that monitors the grid frequency and phase angle, and it do it in a real time. And it's happened across a very wide geographic kind of like grid. So this synchrophaser basically measure the health of the power grid. And they do that by tracking the voltage and current patterns. Okay, so in real time and over the long distances, we could make sure that we have a stability and the performance that we need for that grid. Now, another aspect, like for example, in the smart grid, is the protection system. Now we have relays and circuit breakers and measurement units in the protection system throughout our grid, and they have to have a coordinated actions, okay? Because they use time-stamped voltage and current samples to find the faults or any kind of like fluctuation, so they could respond to that, preventing damages into for our equipment and for our grid. Now, this is not just the engineering work that needs time synchronization. When we talk about the finance, when we talk about like a stock market, okay, high speed financing, then again, time synchronization comes very important. Okay, so when we have like a trading algorithms that basically execute the trading based on the timestamps for each exchange that's happening in the market, then the time synchronization become very important, because when we have like a legal auditing or regulation, which demands, by the way, a nanosecond level logging, we need to know what is the order of those exchanges. So we make sure that we follow the trading in the market, and it happened fairly and in correct order. Now, this is like as you can see, is like a $1 billion kind of like exchange that happening, and it's time synchronization with a good precision is very important in that aspect. Now, when we talk about the time synchronization, there are several protocols that are used in time synchronization. IEEE 1588 work with the Precision Time Protocol, or PTP, which provides like a very accurate time synchronization for the digital systems. But it's not just PTP that we could use. Now, one alternative protocol for time synchronization is NTP, Network Time Protocol. Okay, that NTP offers about like a 1 to 10 millisecond of accuracy. Okay, so It normally used for like a general purposes, okay, like office computers. Okay, NPT is very good for general tasks like your computer's clock scheduling or like email scheduling, okay, but it's not precise enough for industrial or a scientific system that basically needs a near perfect timing. Now, NTP works on a IP networks and it using like internet. So it sends the time updates between the servers and devices through that internet connection. Now, another option that we have for time synchronization is GPS clock. Now, GPS clocks offer around 1 to 30 nanoseconds of the accuracy. And as you probably know that it works by receiving the time signals from the satellite. So the GPS receivers basically can work incredibly precise. Okay, it is one of the most accurate and precise timing synchronization method that we have currently in our technology, in current technology. And this is like similar to how your phone or your car get the locations. Okay, so the downside is that they require a satellite signal. Okay, it happened normally using the through an external antenna. Okay, so basically because GPS needs a clear signal from the sky, it may not work properly in indoor uses or underground. Okay, so the hardware setup can be expensive. So this is one of the downside when we wanted to like compare the GPS method to the other methods that we have, the other options that we have for time synchronization. Now, another option is synchronous Ethernet, or what we call it a sync E. Now, that provides a frequency synchronization. Okay, it's not a complete time synchronization. It's a frequency synchronization. Okay, so it basically ensures that all the devices tick with the same speed. So it doesn't actually align the time. It's mostly for the frequency and the speed of the clock ticking, basically. Now, this sync E works directly with the hardware, okay, and transmit the timing, most of the frequency of the timing using the electrical signals in the cables. Work well in a core telecom networks, but it's not flexible for like general computing systems. Now, let's talk about our main topic that we are going to discuss today, which is another time synchronization method that we call it Precision Time Protocol, PTP, covered by IEEE 1588. Now, PTP provide the synchronization with less than 100 nanoseconds. Okay. Now, this precision is based on the complexity of our network and the level of the traffic that we have in our networks. And it does that in real time. And it's very good for distributed systems. So it is much more accurate than NTP. You can see that it's close to like a 1,000 times more accurate than NTP. And it's nearly work as good as GPS, not better than GPS, but it's near. The precision is near. But the upside for the GPS is comparing the GPS is that it doesn't need satellite or expensive kind of like hardware configuration. So it's work just in a regular network. Now, that PTP, one of the good aspects of the PTP is that it can work over the Ethernet or IP protocol. Okay, so it has the good features of the NTP and good precision, nearly good precision of the GPS. Okay, so basically, it could adopt in a different kind of like system needs. This is a very versatile kind of like flexibility that make them able to like work over standard local networks or even over the internet. So depending how you want to set up the system. Another good features of the PTP is that it supports both hardware and software time stepping. So we could have high precision in both aspects. Okay, now PTP is very flexible. When we talk about supporting like a network that are flat, we are going to talk about what we mean by flat network, or the network that we have a hierarchy in our system. So we have like several layers in our network. Uh, now, now that we talked about the options that we have, let's focus on the standard that we want to talk about, the IEEE 1588. Now, the protocol in IEEE 1588 is basically designed to address the accuracy, scalability, and the flexibility at the same time. Okay, so uh, it uses message exchange between the master and the slave clocks to synchronize the time over the network. And like instead of the hard wiring time signal, like the older systems, it works by sending in a special message, basically a timing message. We are going to talk about the type of the message and the structure of that message later on, like a digital letter. Okay. Now, it happened back and forth between the devices at the same network cables and the same connection that you use for the regular payload data that you have and you want to transmit in your system. Now, as we said, it could work both using the Ethernet, which you might know it as a layer 2 network, or IP, which you might know it as a layer 3 networks, which means it's highly flexible and it can be used in both like a local connections and like a broader networks based on like internet-based networks. Now, another aspect that we have to mention when we talk about the IEEE 1588 is the hardware time stamping. Now, the PTP basically can mark the messages, okay, at the hardware level with a precise time stamping. So instead of relying on the computer's operating system, which might be in a high traffic, high processing situation, it could be like a very busy and with like a high level of delay, we can use the time synchronization in hardware level. So it captures the exact time a message leaves or enters the device. Now, basically, this aspect reduces the time errors, which basically caused by operating system delays and makes the synchronization more accurate. And that's one of the reasons that we have like around like a nanosecond accuracy and precision when we're talking about the PTP. Now, one of the very important aspects that we have in the PTP in IEEE 1588 is clock roll negotiation. We are going to talk about that. That's because like we have several clock in our network, and each of them has a specific role in the time synchronization. But how we kind of like assign these roles when we talk about the PTP is one of the best features of IEEE 1588. Now, PTP uses algorithm named Best Master Clock Algorithm. The acronym is BMCA, and it automatically chooses the most accurate clock in our network. So it's like the devices, all the devices that are connected to each other talk to each other, and they automatically decide who's the most precise clock and assign it as a grandmaster to follow the time based on that device. There is no manual intervention when we talk about the clock roll negotiation, so it happens automatically in the system. So this is a very good feature when we talk about the PTP. Now, another aspect that IEEE 1588 works on it is the delay compensation. Okay, so when you have a network, we definitely will have delay when we wanted to like send the timing messages and the synchronization messages between our master and all the devices through the network. The delay would happen. It could be the delay like because of the medium that we have to like send a message, or as we said, there is like a delay in the processing and operating systems that works in the devices. Now, what PTP offers, what IEEE 1588 offers, is that it offers several methodology and several like algorithm that you could actually compensate. You can find those delay and compensate for the time that takes for a message to travel across the network. Now, uh, it uses strategies like delay request response or peer-to-peer measurement. So it could correct for both fixed and variable delay. So it's not like an offset delay. Sometimes we have the error in the frequency when we have several devices. Each of them has their own clock. We cannot guarantee that all the clocks would work at the same frequency and the same kind of like a speed, like a ticking a speed. So there is an offset caused by the operating system, like a static error caused by the operating system and the medium. But we have like a variable delays, which caused by the differences between the speed of the clocks, which basically create an accumulated errors when we talk about the time synchronization through the time. Now, to avoid those, PTP basically sends some extra messages that actually help to detect and cancel those delays. Okay, so when you have like a very long cable, very wide network grid, this will be like an essential aspect actually in time synchronization. Now, IEEE 1588 is not a one-fit-all task. Okay, we have several complementary standards that are defined based on a specific application of times when we talk about the time synchronization. So 1588 is a ground, is the foundation. Now you have to realize if there is a specified complementary standard when we talk about the time synchronization in your field, and if there is, you need to adopt the requirement or the methodology on that alongside the requirement and definitions of the IEEE 1588. One example would be IEEE 802 Part 1 Substandard 8S. Now, this is a generalized PTP. We call it GPTP. Is like a specialized version of IEEE 1588 when we talk about the time-sensitive networking. So this version basically used in the networks where precise timing, we need that precise timing for things like audio or video streaming or industrial automation. So we could make sure that the devices stay tightly synchronized. Now, another aspect which covers the telecom profiles is the standard that we have ITU-T G8275 substandard X. Now, that standard, that G8275.X, basically defines the PTP profiles that is used in a telecom networks. Okay, when this is basically give us the ability to distribute both time and phase information. Okay, so these are detailed guidelines when we talk about data standards of how telecom providers like Verizon or AT&T in United States should use the PTP so they could make sure that they're keeping their system synchronized down to like the a fraction of microsecond and like a nanosecond scale. Now, this is very critical for technologies like 5G and LTE. And for example, if the cell towers are not perfectly synchronized, your mobile phone calls and the data may drop or lag. So this standard and the complementary requirement that exists in that standard basically make sure that everything runs smoothly. We have another standard for like substation automation, IEC 61850-9-3, which is used in the power grid substations to synchronize the data from the electrical devices in our grid. That makes sure the voltage and current measurement that are taken from different parts in the power station all have the same time reference, which is very important when we talk about the safety and efficiency of the power grid. Now, as we mentioned before, the protection system in the power grid also heavily relies on the time synchronization. So the relays and phasor measurement units, you might know it as a PMUs, they make sure that those devices have like are able to like make accurate decisions based on that synchronized data. Now, we have SMPTE ST 2059, which normally used in and covers the broadcast and studio applications. It synchronized the clocks in like a professional video and audio production environment and prevents problem like audio video desynchronization and enables like precise switching between the video feeds. So basically it's make the viewers to not notice any delay or glitches when we talk about the broadcasting and ensures like a seamless production. Now, as we said, IEEE 1588 is a core part. Okay, so it's not isolated technology, it's a part of that global system of time synchronization. Now, it's a foundation. Instead of being, as we said, one size fits all solution, that PTP acts like a flexible foundation, and other standards could be complementary and built upon that specification to meet some specific timing needs. Now, but we talked about the IEEE 1588, the importance of the time synchronization. Let's see what happened through the time on the evolution of the time synchronization, where we started and now where we are right now. Now, when we had like the earliest version of digital systems, the time synchronization normally was achieved by sending like a hardwire electrical signals directly between the devices. Okay, so uh, this has happened before the computers were connected by networks. So the devices need to work in sync using physical cables that carry the timing pulses from a central source to each system. Now, we had pulse per second signals that was generated, like for example, from atomic clocks and used for this like direct coordination. And this method worked good enough, but wasn't scalable or flexible when we talk about a large or a dynamic network. So that was the shortcoming of that PPS methodology in early state of the digital technology and digital system. Now, after that, to address some of those shortcomings, we had the NTP, the Network Time Protocol, that was introduced in 80s, and it was the purpose was to synchronize the time over the internet, so we could use a packet-based communication. So it would fix the scalability problem that the PPS had. So the NTP uses a software time stamping. So, and as we said, the precision is around like 10 to 100 millisecond, which is one of the shortcomings of the NTP. And if we have like a local small networks, we could reduce that precision to 1 millisecond. Okay, but it's still not good enough when we talk about some of the high tech and very sensitive, time sensitive systems. Now, to address that lack of accuracy and precision, the GPS receivers and the GPS time synchronization was introduced into the technology. So it provided a very high accurate timing and was used using the signals from the satellites. Now, devices can use GPS to get very precise time, like your phone or like your car, as we mentioned. Now, we have another method which is close to the GPS, and it was developed at the same time. This is like we call it IRIG-B, another method that delivers time codes over that works over coaxial cables. Okay, that method, and it synchronizes the devices using that. Normally, it used for like the military and industrial system, and it is kind of like, as we said, it uses the coaxial cable and sends the timing information through that system. But these technologies, when we talk about a very large kind of like network and a very wide geographic kind of like distribution of our devices, then they have problem. That IRIG-B, since it works over the cable, it doesn't have the ability of the scalability. It answers the precision, but it doesn't have the scalability feature. And the downside of the GPS can be used on a scale on a large distributed system because it uses the satellite to transfer the data and receive and send and receive the timing messages. But as we mentioned before, it needs certain like a hardware configuration that could be expensive in some cases. So, and it doesn't work as precise as it should be in an indoors or underground situation. Now, to address those shortcomings, the time synchronization was evolved, and the IEEE 1588 was introduced to define the precision time protocol, PTP, so we could deliver like a very accurate time synchronization, as we said, like is down to a few nanoseconds, not as precise as GPS, but it is close, and it worked over like a Ethernet networks or IP-based networks. So it covers also the scalability problem. We didn't have because of that methodology. Now we don't have the hardware, the expensive hardware configuration that we needed for the GPS. We have nearly the same precision, and also we have the good feature of the scalability from both NTP and GPS methodology. So there are some key roles within the PTP system. Okay, so there are some the key roles that the devices should take, like each device assigned as a certain role in the system that we have to know. The most important one is the grandmaster clock, which is basically the master or like the clock with the highest precision and is the main source of our time synchronization messages. So it should be the most accurate time reference. We could use like a GPS as the grandmaster or like an atomic clock as the grandmaster. And only, but you have to pay attention. In each system, we only have one active grandmaster. Okay, so at a time. Okay, so they could change the roles between the clocks, but at each time we have one grandmaster. Okay, and as we said, one of the good features of the PTP is that they negotiate between themselves, the devices, and they automatically assign the role of grandmaster clock to the most accurate device by using the best master clock algorithm that we mentioned. So this is like the definition and the role of the grand master clock. Now, we have some ordinary clock in our system. There is another role in our PTP system. Those ordinary clock has just like a one PTP communication port, and basically can either send the time or receive the time, depend on the situation. These are like typically simple devices like sensors or like cameras or PLCs that either give or take the time information in the networks. Now, ordinary clocks are normally at the edges of the networks. Okay, so where the devices need to accurate timing to perform the tasks that they have. And for example, a camera in a factory might need a precise timing to timestamp the images. So the action could be taken based on those information. Now, another important and main component role in the PTP system is the slave clocks. You can imagine what is the role of the slave clock, which basically receives the time from the master or grandmaster, so it could adjust their internal time to match the grandmaster. So slave clocks are the client. Okay, so in our system. So they are followers, okay, and they listen to the leader and keep correcting their internal clock. Now, those slaves should be continuously measure the time difference and correct both clocks and the frequency uh, following the grandmaster. Now, these are the three foundational roles that we have in a PTP system. There are some other roles, okay, in our PTP system, like a boundary clock, which boundary clock has like a multiple PTP source. You can see this is the difference between the boundary clock and ordinary clock. It has multiple PTP source, and it could act both as a slave. So in one port, it receives the data from the grandmaster, and as a master for the others, so it could send the data to the other devices. Now, this helps when we have a very a wide network. Okay, so we could have like a hierarchy in our system, several layers in our PTP system, and basically isolate the sections in our system with each other so they would not affect the time synchronization of each other. So, for example, we have one grandmaster, which is the reference. It would send the signal to the boundary clocks. Each boundary clocks manages a certain section in the whole network, and it acts as the master for that section. Okay, it received the data from the grandmaster and act as a master for its own section. So we could isolate different sections in our system. Now, it's normally used in a PTP aware switches or routers. So in practice, the network switches themselves can become like an intelligent participant when we talk about the time synchronization. Now, another role that exists is the transparent clock. Now, transparent clock forwards the PTP messages without any change. But it adds a correction value to count for the time that the message is spent inside the device. Okay, so imagine like a mail carrier who doesn't open the letter, but writes on the envelope how long the letter was delayed inside the post office. Now, the transparent clocks are typically, you can find them in a modern Ethernet switches that are not fully PTP aware. And they are a part of our wide area networks. Now, another role for the devices in the PTP system is management node and PTP monitor. Now, those management nodes are observers. They only monitor the behavior within our PTP system. So they only observe the clocks. They are not an active participant in our system. So it's mostly like a supervisor watching how well the system works. So if there is any problem, we can address that problem in our system. Now, measurement nodes are very important when we talk about the synchronization quality, and when we talk about the system health. So basically, it's ensures the reliability of our time synchronization or our PTP system. Now, within our PTP system, we have some synchronization model that we have to follow or we have to use. One would be the clock offset. Now, the clock offset is the difference between the time on the slave and the time on the master. Okay, so basically PTP's goal is to minimize that offset. So it's continuously adjusting the slave clock to match the master time. It exchanges the time messages. Okay, so it would detect how far off the slaves are and then nudges it back to align with the master. Another aspect that we have to pay attention when we talk about the synchronization model is the path delay. We mentioned that briefly. Now, the path delay is the time that it takes for a PTP message to travel from one device to another. Okay? Basically, PTP estimates this delay. Okay? And it does that using a special message exchange so they could adjust the clock synchronization so they could account for that delay. Now, past delays include like a multiple source, like cable length, signal propagation, uh, or like a processing time in the devices. As we mentioned, the errors is not just the static and offset errors. We have some time-dependent errors, which is, we call it the clock drift. Now, the clock drift is like a gradual difference, which is caused by the ticking speed, the difference in the ticking speed between the two clocks. It's because of the imperfection in the hardware. It happens that. So even if two clocks start with the same time, okay, because of that drift problem, the clock drift problem, eventually they are going to be out of synchronization. So how we address that? The PTP uses like a servo algorithm. So it's continuously monitor and correct for the clock drift by adjusting the slave's frequency and time. So it's not just the time, okay? Now, we said that PTP synchronize the system based on exchanging some message. But what are the message exchange paradigm, okay, that we have in the PTP? We have either one-step paradigm or two-step clock paradigm. Now, what is the one-step? One-step clock basically puts the exact timestamp directly into the synchronization message. Okay? So basically it does that at the moment it sends the message from the sender, and it uses like a special hardware kind of like situation, configuration. Now it requires advanced hardware, but it reduces the message overhead because it doesn't need a second message. So it does that through one message. Now, on the other hand, we have two-step clocks paradigm. That one first sends the synchronization message, and then it follows with a separate follow-up message. That follow-up message contains that accurate timestamp. So it's like sending a text saying, I just mailed you the letter, and then later on send another kind of like a follow-up text that it says, actually, I mailed it that on that exact this time. Okay, so something like that. So this allows the timestamp to be captured more accurately at the hardware level, and is basically try to avoid the delays caused by the operation system. Now, there is another paradigm that might use, and it's a 4 timestamp model. We call it end-to-end. On that paradigm, the PTP use 4 timestamp process between the master and the slaves. Okay, so basically the clock this measures when the master sends a synchronization message, when the slave received that, okay, when the slave send a delay request to the master, and when the master receives that response. We show it by like T1, T2, T2, T3, and T4, and then the clock offset is calculated based on those times using like a very simple a formula that you can see in the slide. So this formula basically compares those time that took the messages to travel each way, okay, and basically estimates how far the slave clocks is behind or ahead of the master. Now, this method is, you have to pay attention. This method is only accurate because of the formula. You can imagine that if we have the same delay in both directions. So basically, it needs the system symmetry when we talk about the delays. Now, we talked about the paradigms. Now let's talk about the PTP domains and port states. Now, PTP domain numbers basically create a logical group of clocks that synchronize with each other. So think of it like a PTP domain like a private clock where all the clocks follow one grandmaster. So the devices in the same domain synchronize with each other and ignores the clocks from another domain. Okay, now multiple PTP domains can coexist at the same physical network and without any interfering actually with each other. Like multiple group chats can happen over the same Wi-Fi. Several PTP systems can run side by side on the same cable, and each staying in its own lane using the domain numbers. So they code their domain by the domain numbers. This separation allows the different system to maintain their own independent timing. Now, we have some PTP port states, which basically PTP devices has ports, those network connection that we have on the devices, and they can behave differently in different ways depending on the roles that the device has. We talked about the roles before, so based on the roles, those ports could take different state. It could be master, which it sends the synchronization message and the follow-up messages, basically in a 1-step and 2-step paradigm that we talk about. And it basically distributes the time to the devices. Now, that master state is not only used for the grandmaster. We talked about that. The boundary clocks works as the slave of the grandmaster, but in their own section works as a master for their slave devices. So these master ports are the sending ports of the grandmaster. So the grandmaster has only the sending kind of port, and the boundary clock also has the sending port and receiving port. Now, Another state that the ports in the device can take is the slave state. Now, those ports that are assigned as a slave ports are the ports that receives the synchronization message and try to adjust the clock using those messages. Now, we have some passive ports in our networks, which those ports just listen to the message. They do not send any message or use those messages for the synchronization. We already talked about that. We have some management nodes that they are only observer. They are not active participant in the PTP system. So these passive modes, these passive states for the ports are used for that monitoring and management nodes. Now, also we have listening states, which basically is the port is waiting and monitoring to see who the best clock is. Okay, so that listening ports, they are not for management nodes. They are used for that best master clock algorithm. So these ports are tied to that feature of that automatic negotiation feature that we said that PTP has, so they could choose the grandmaster between all the devices. Now, another state of the port, which is obviously one of the states, which is a disabled state. So the port is completely inactive and it doesn't involve in a synchronization. It doesn't listen, it doesn't monitor, it doesn't send or receive any messages. So these are the disabled ports that exist in our system. Now, so far, we talked about the protocols for time synchronization. We talked about the PTP and its features, the pros and cons of the PTP. We talked about how the PTP works, what are the rules of the PTP. We talked about the paradigm that the PTP works, that one step and two step. And we talked about the ports. Now let's talk about the architecture of those components. We already covers those roles. Let's talk about the architecture of those, how those components, how those roles connect to each other and create that PTP system. Now, we said we have the ordinary clocks. We share the devices with a single network ports that either sends time as a master or receive time as a slave. So these are the simplest participant in a PTP system. And like sensors or cameras, which either they follow a time source or become one of, if it has the best clock, one of the masters, okay, or the grandmasters. So they commonly are in the edge of the network. So then the accurate timing is needed. Now, another component in architecture is the boundary clock, as we mentioned, which connect multiple parts of the network, okay, and passes the synchronized time from one side to other. Now, we said this helps the large to divide the large network to the smaller networks. By doing that, we can keep the sections, the different sections, isolated from each other, so they would not affect each other. And at the same time, when we basically keep that layer between the grandmaster and all the devices, we basically reduce the load on the grandmaster. So now the grandmaster has to deal with fewer devices when we're talking about the synchronization, which helps a lot when we talk about the delays and the precision of the time. We said that if we have like a less traffic, we could have a more precision in our system. We have transparent clocks, which basically forwards the PTP message. It doesn't change the PTP message, but it adds a correction message for the time that message is pinned inside the device. and basically compensating the internal processing delays and improve the precision of synchronization across the network when we have mm, multiple or like very high number of like switches in our system. We mentioned the basically the most important role, which is the grandmaster clock, is one of the component in our system, which is the basically the top of the level. It's like the reference, topmost reference in our PTP network, and it's the main clock. So it's typically synchronized to the high accuracy source because it's the extremely precise and stable clock between the whole devices in the network. Management nodes are another component, as we mentioned in the architecture, which basically are the observers of the system. So they follow up how good the PTP system works, how well it works, and how precise it is. So we can observe the system health and the efficiency of the system. And if we need to optimize or interfere or like issue some address some issues, we could have the data to act based on them. Now, all these components can connect to each other through different architecture kind of like options. Okay, we could have flat architecture, which is when all the PTP devices are directly connected to the grandmaster, and they are in the same network. So we don't have the hierarchy, the layers of connection. Grandmaster is directly distributing the time to all the devices. The flat network normally is good for a small or like a simple installation. Like, for example, when we have like a single factory floor or like a small AV system. But the problem with the flat architecture that it doesn't scale. So when we have a large or distributed system, that type of architecture would have a problem like regarding the network congestion and like the timing degradation. So the bigger the setup, so it means the too many devices receive the message directly from one grandmaster can cause delays, errors, or the synchronization breakdowns. Now, another option that we have is to have a hierarchy in our architecture. We talk about the boundary clocks, and we said, okay, they are going to sit between the master and all the devices. Now, it's not like we have only one layer of the boundary clocks. We could have a very wide hierarchy, like several layers of the boundary clocks to reduce the traffic for each devices and the load for each devices. And basically, this setup is like a company structure. So we have a hierarchy in our system. The grandmaster sits on the top. It would send the messages to the boundary clocks. Each boundary clock is responsible for a certain section or a certain group of devices, which basically transfers what the message that is received from the grandmaster to the devices that is connected to that specific boundary clocks. As we said, it reduces the load on the grandmaster, basically by limiting how many devices are connected to the grandmaster, and improves the scalability and also helps isolating timing problem between the sections that we have in our system. Now, we might have another option of the architecture that we have actually another option of the architecture, which we call it a mixed architecture, with the transparent clocks, that mixed architecture uses the transparent clocks between the devices, so it would improve the timing precision. Now, we talk about that when we have like a GPS system or like a PTP system, they have a limitation on how precise they could work on a time synchronization. We said like in a PTP we could have like a 10 to 30 kind of like nanosecond precision. In GPS, sorry, in GPS we could have like a less than a 30 nanosecond precision. In PTP is slightly more, like but up to 100 nanosecond. Now, if we need a more accurate precision, better than those that are offered by those grandmaster clocks on those systems, those methods, now this mixed architecture could help us. How it could help us? When we have the transparent clocks between the devices, it basically improves the precision. So it means like when the message pass through switches or the rotors, those devices basically report how long they delayed the message. Now, this could happen also in the grandmaster, because you request a timing message as a device, as a slave, to the master. Now, the process of sending, creating the time message in the grandmaster and sending it back to the slaves, this is not like a zero second. It still take time. Now, that transparent clock in the grandmaster count for that, creating kind of like offering a compensation information to increase the precision on our time synchronization. And they don't generate or consume time. They just try to remove the hidden delays in the system, in the internal system. Now, we talked about the component and the architecture, and we said this synchronization happened by sending some synchronization messages or some delay request or a delay response or follow-up messages. We already mentioned those in our previous slides, but let's talk about what are the type of the messages that we have in our PTP system. Now, we have three categories: synchronization, announcement management, and optional P2P, peer-to-peer. Now, when we talk about the synchronization message, we have four different type of messages. Our message could be like the synchronization message that is sent by the master clock to mark the current clock. And it's basically a start the synchronization process, that synchronization message. Another type of the synchronization category is follow-up message. We said in a two-time clocks, the two-step clocks paradigm, we have a follow-up message that is following that sync message. It's sent right after the sync message and basically provides the exact timestamp for that sync message. So we don't contain the timestamp inside the sync message. We send another message to say, okay, that sync message that you received, I send it in that exact time. Now, we mentioned the four-step paradigm, and we send like sometimes on those paradigm, the slaves send a request to consider the delay, and the grandmaster or the master, the boundary clocks, would respond to that. So that process has two type of message. One is the delay request, which basically the slave device send a message to the master to ask how long messages take to travel through the network. Now, after it's like asking how long did it take my message to reach you. So I can factor that into my clock setting. Now, master would respond to that request by delay response type of the message. And it's basically the answer of the message that says to the slave that, okay, I got your request at this specific time. Now, the slaves know, it knows, okay, I send the message at this time based on my clock. The master received that in the the T2 time. So the delay in our connection could be calculated based on that 2 times. Uh, and this is the complementary kind of information because we already have the synchronization message and follow-up message that could also be used for the calculating the time delay. That delay request and delay response is basically give us more information. It's like a probabilistic kind of analysis, more information to more accurately we could kind of decide how much delay we had in our system now or estimate that. Another category that we said is announcement and management messages. In that category, we have 3 types of messages. One is the announce message. That is used by all the PTP clocks. So they advertise their quality and the readiness to become the grandmaster. Okay. The management message are used to control and monitor the PTP devices. It doesn't affect the time synchronization. It's a passive kind of message. And we also have the signaling message that basically carries extra information when we talk about some specialized feature, and it helps path tracing or a unicast negotiation when we have in our system. It's like sending an extra notes between the devices that says here's an alternative path, or let's switch to a private communication. This is how the devices talk to each other to improve and optimize their PTP process. Now, we said there are some optional peer-to-peer messages. One is the peer delay request. This is normally used between the 2 directly connected devices. So it's like asking your next door neighbor of how long does it take a message to go between us directly. Now, when you send that request, you will get a response, which is the peer delay response message, which basically says that I got your message, that request at this exact time, so it could help to calculate one-way delay accurately. Now, we have peer delay response follow-up, which is used to timestamp that response that we sent. It's like the follow-up message in the synchronization. And it basically says that, okay, the response that you get was sent at exactly this time. Now we know those message types. Let's talk about how the system would exchange those messages. There are 2 models to exchange those messages. One is end-to-end model, E2E. Another one is peer-to-peer model, P2P. Now, the end-to-end model is normally used in the networks that have an ordinary clock and boundary clocks. Basically, this is common in a system where each device is connected through layers. So we have a hierarchy, and timing should be passed from one clock to another clock through that chain. Okay, so It normally uses the four type of the messages: the synchronization message, the follow-up message, the delay request, and the delay response. So they could measure the delays and synchronize the clocks. That, as we said, this is kind of like the two-step delay. When we talk about that T1, T2, T3, T4 aspect of this type of exchange models, this E2E model has the fun has one of has a fundamental assumption which says that the delay is symmetric, meaning the time from the master to the slaves equals the time from slaves to master. But this type of like E2E is normally used in like a automation or like a enterprise IT systems, and the network that had relatively stable traffic. So uh, why we say that a network with a stable traffic? So imagine we send the data from the master in a low traffic situation to the slave. So definitely it would take less time. And when the a slave wanted to like send a delay request, we are in a high traffic situation or higher traffic situation. So it takes more time. So it's break that symmetry that we talked about for the end-to-end model. So you cannot. It's not good for. Uh, it's not good using that model in a system that doesn't have like a relatively stable traffic patterns. Now, the second model that we mentioned is the peer-to-peer model, which is the P2P. We call it P2P. This is normally used in a network that has transparent clock, like advanced switches or routers. We talk about that it uses the P delay request, the peer delay request, or peer delay response, and like the peer delay response follow-up messages that we talked about. It's directly measure the delay between the devices that are neighbor to each other, directly connected to each other. And basically, instead of calculating the round trip delay for the whole pass, now we could measure the each link individually. So it's more accurate delay data for estimating that offset connection or like the drift that we have in our clocks, between our clocks. Now, this is more robust. This model is more robust when we have like asymmetric delays, okay? And we have like a variation in network traffic. And it's preferred like in the telecommunications or like a time-sensitive networks and like a multi-hop industrial networks. Now, we talked about those messages and how we exchange them. Let's see, okay, what's inside those messages? When we talk about the synchronization message, what is the structure, the internal structure of those messages? Now, we have three main part in each message. One is common header, then is the payload, and then is the transmission method. Now, the common header basically is the beginning of the messages in a PTV, and it includes like the essential information. So it's like identifying, routing, and processing how those information for each messages. Like think that for that mail situation, like you have an envelope that on the envelope we have the information about the details, like what is the type of the message, who's the sender, what is the version number, and the timing flag, so the devices know how to handle that message. Uh, Now we have also the correction field that exists in that header, which is basically uh, count for the time delay that happen inside the intermediate devices. Okay. Uh, we have like the source port identity in the header. We have the sequence ID in the header, and we have the log message interval also. All this information are inside the header part of the message. Now, we have the payload, which basically is carry the detail of the timing data or some like extra information like type, length value format. Okay, so like this is that TLV is like attachment that specify additional function like requesting a different time source or like tracing the message path or negotiating like a unicast communication. Now, after that main data, the payload, we have the transmission method part, which basically we know that we can transmit like in a different way. The transmitted data in a different way, it could be like a multicast or unicast. So that actually defines how that message intended to be transferred between the devices. Now, we talked about those. Let's go over like an example to kind of make sure we understand everything. Let's consider this scenario. Like we have like a smartphone factory. That smartphone factory has like a robots that assembles parts. We have cameras to inspect the screens. We have sensors that checks the temperature. We have a central server, basically logs the events, and a control center that coordinate everything. Now, so these are the main component in our system, and we want to have them perfectly in synchronization. Now, to address that, since we have a wide network and each network has its own purpose, the best option for architecture of the PTP system that we want to use is that hierarchy part. Okay, so the architecture with the hierarchy. So, for example, in this system, we structure a three-layer synchronization hierarchy. The top layer is gonna be the grandmaster. It could be like an atomic reference that distribute basically the time synchronization, time across the system. Uh, it is gonna be placed in the control center because the control system coordinate the whole system in our factory. Then, because we have a hierarchy, we said that the next layer after the grandmaster is gonna be the boundary clocks. Okay, that divide the system to the sections and segments. Now, these could be like the PTP aware switches that has multiple ports and basically transfer the data from the GME, receive the data from the grandmaster, and then send it to the downstream ordering clocks. And basically recalculate the time at each hop to minimize the accumulated errors. And in the bottom layer, we have our clients, the ordering clocks, that basically receive. So it could be those robots or cameras or sensors or the server that logs the information that basically has only one PTP port that acts as a slave in our architecture. Now, we said we have several type of a device in our system, as we said, you can imagine that the robots are a slave, the cameras, sensors, and beside the grandmaster, the control server are also the slaves. So the they it is kind of like obvious that they are going to use the information in synchronization message to align with each other. Now, because we have like a relatively a low network, we can use like the end-to-end synchronization exchange model. Basically, we send the synchronization message as time 1, the follow-up message at time 2, the slave send the request, the delay request at time 3, and then the master responds to that at time 4. So we could use that formula that we have to calculate or estimate the delay. And it's not, as we said, end-to-end assumes the symmetry in our system, which is not quite off the part, because in a factory we have like quite a stable traffic pattern, so we can use that assumption to simplify our system and use the end-to-end model. Now, what are the benefit of that model that we describe is that, first of all, when we talk about the robots, the motion controls basically receive the synchronization ticks, which eliminate the jitter and prevent like a spatial misalignment. Cameras that works for the quality control become aligned with the mechanical steps. So we have a real-time visual inspection. And we can have like a deterministic accuracy when we talk about the quality control in our factory. Now we have environmental monitoring, those temperature sensors, which by this architecture, we have a precise timestamp data. So we could have like correlation between the operational anomalies and like the environmental condition. Okay, so the server that we had that logs the data would have, again, the precise timestamping. So it would logs the data in a accurate order, in a good order. So when we wanted to like have a legal or regulatory kind of like audition, or we want to have like a forensic traceability analysis, we can rely on those timestamp and the data. So basically that PTP transforms that factory into like a high performance, fully synchronized and time-aware cyber physical system. So this is our discussion. If you have any question, please let me know. Otherwise, thank you for your attention to this topic.